So, okay. So, let us sort of continue from there. Okay. So, the way we discussed that waves are basically produced by a perturbation over ambient conditions, right. So, we said that if you have for example, say if I were to plot say okay, so for this and say this is say density, right. So, density and say at some time say t1. Okay. This is at some time, this is a picture that you are seeing at say some time t is equal to t1. So, if I have a ambient conditions of say gamma infinity, then at some point due to an impulse I have a certain disturbance which is in the introduced into this ambient conditions. Okay. And then, so we said delta gamma, and we can have the same picture for pressures, velocities, etc. Okay. Now, then what we said also was that if I look at the same plot at say at another time instant, which is at an advanced time. So, then again what happens is that this disturbance also travels. Okay. Again this is gamma infinity, this distance also travels, but now it looks different as well. Okay. So, say right, it looks different as well. So, again, so therefore, if I possibly took a reference frame say here, okay, at the start of this okay. So, if I took a reference frame at the point where the disturbance has started. Okay. So, I will take the same thing over here, right. Okay. Then if I say I take a particle, if I take a particle, call that as particle A. Now, that particle is at a different location at time t is equal to t2. Right. So, what we are basically trying to say here that particles within this disturbance move differently. Okay. So, they also each particle is moving differently within this disturbance. Okay. All right. Now, mathematically what we said that the governing equations, okay, the governing equations, the continuity, conservation of momentum and the energy equation. So, if I if I introduce the perturbations into that. Okay. If I say that the density term is the total density is actually the ambient density plus an induced perturbation, right. So, that gives me the total density, because the local velocity, the local density velocity here is basically due to this perturbation, right. But the total velocity density is basically when you add this local velocity to the ambient conditions, isn't it? That is what you will see. So, here this is the delta t, isn't it? So, at this for A for example, okay, for A for example, this is the perturbation, or this is the change in the, this is the density when I consider it just within this wave, or just within this disturbance. So, now the total density however here is when I add the ambient condition to that. So, therefore, I get a total density of gamma infinity plus this. So, similarly we can have the and so on and so forth. Okay. So, in our derivations yesterday in the last lecture, what we did is that we said this was initially at rest. So, we said initially this was at rest. So, therefore, the entire change in the velocity is happening because of the disturbance of the wave. Okay. So, now what we did was we introduced these perturbations into the governing equations, and what we came up with was well, it was slightly a large sort of equation, but I will go ahead and write that. Okay. So, what I came up with was this. Okay. So, we came up this from the continuity equation, okay, and from the momentum conservation and energy equation, we came up with this. Okay, so this is okay. So, we actually essentially have quite an extensive okay. So, that is enough to confuse us, right. So, we have this, let us call that as say 1 and okay. So, we said finite waves. What are finite waves? When this perturbation is finite. Okay. So, it is not very small, or it is not something that you will ignore. So, you do have a finite perturbation. So, you have a finite wave. So, for this picture out here, the governing equations are basically this. So, this is the continuity, and this is a combination of the momentum and the energy equation. So, this is what we get. So, now we saw, if you look at this, so now what we said, okay, now this seems to be too complicated. So, let us do one thing. Let us consider this to be a very weak wave, okay, like a sound wave, and what we will do there is we will go ahead and say that delta rho, all these perturbations, etc. Okay. So, for example, is very, very small. So, this is very, very small, then delta u is very, very small. Okay. So, essentially what we are saying is that if you have a wave like this, okay, where there is a finite disturbance and or perturbation, then you have these are the governing equation. Instead, if you have something like this and you say, okay, you have say a disturbance, say you have a disturbance like this. So, as you can see, if you say look at this part here. Okay. So, if you look at this part here, okay. So, in here this is my delta rho say. So, you can, so let us call this as say dash. So, if you look at this clearly, okay, so this disturbance or perturbation is very small. So, for this particular case we will just ignore it, and we will say that the perturbation is really very small. Then what do we do? In that case, how does that get taken care of in here? So, there is a perturbation, it is very small. So, therefore, it is a very weak wave. Okay, there is a very weak wave. So, in that case, what do? what happened in that case was that we were able to reduce again these equations or transform these equations in the following way. So, our continuity equation becomes this. This is from the continuity equation. Okay. So, what we have here is, so let us say I am going to call this as 1 dash, because this is what we get from 2 dash. So, this is, so essentially if I assume this, then my continuity equation gets transformed accordingly, and the other equation gets transformed in this fashion. Now, these are therefore, because we said it is a very weak wave, it is like a sound wave. So, therefore, these are acoustic waves. Okay. These are acoustic waves. Okay. And the important thing here is that you can see here that I had an extensive nonlinear equation, okay, and I have been able to convert that to a linear set of equations when I consider a very weak wave. Okay. Now, there is another advantage to this. Okay. Okay. I think I may have kind of done this last time probably. Yeah, I think I have done this, right. So, essentially what we then came up with is for a solution of this. Okay. I came up with a solution for this, where I said that now if you make combinations of this and so forth. So, if I combine these two equations suitably, then I will get these two equations. I will get basically these two equations. Okay. And so, if I combine these two suitably, then I get these two equations. Now, these two equations mathematically are termed as the wave equations, and they have a defined solution to them, right. So, say in this particular case, so therefore, if I have an equation of this form mathematically, say of any say parameter, say phi, let us just call that. So, that is so if I have say something like this, right. So, this is a wave equation, and this has a solution of this nature. So, this has a solution of this nature. This. Okay. So, therefore, what we get from here also is a solution like this, right. So, which is that delta rho is okay, and delta u is again. So, this f, all these f's etcetera is are basically arbitrary functions. Okay. So, what I essentially have therefore is that numerically now, if I have basically solved my governing equations using the perturbation theory for small perturbations, I have been able to linearize these equations, and from there I get a solution for these equations like this. Okay. Now, let us just see what this how does that change actually this picture. Okay. I have a wave here, I have a wave like this. So, in this case just this perturbation is slightly very small. Okay. So, for this the governing equations using the perturbation is this. I was able to assume that I was able to basically say that this is a weak wave. So, consider these as very small, and so therefore, I get a solution for the perturbation in this form. So, how does that now, based on this solution, how does that change the picture that we have been dealing with so far? Now, to do that, let us do this. Okay. So, for that, now let us say first things first, we will say that say G is 0. Okay. So, let us consider these two solutions over here. Okay. So, let us say, so we will take this. Okay. So, having taken this, so essentially what we are saying is that delta rho is okay. So, now let us say okay. So, therefore, what we have is okay. So, if I have that, now let us say this delta rho is also a constant. Now, say this is also a constant. So, let us call that as say delta rho naught, let us call it that. So, in that case, if that is so, then let us call that as let us call that as C. Okay. So, essentially, so delta rho is a constant. Okay. So, in that case, this is an arbitrary function. So, therefore, this also becomes constant. Let us call that as C. Okay. Now, what we see from here is that if you look at this term here, now this relationship here was basically giving us the relationship of the perturbation with respect to space and time. And as we saw in the finite wave, that this actually the way the particle moves within the wave is different at different times, and it changes at different space also, which is one dimensional x time, right. So, essentially this is giving us how the wave is traveling, how a particle within the wave is traveling. So, what I see over here from this relationship, that the way the particle moves within the wave is actually a straight line, isn't it? If you look at this, it actually moves like this, and if I look at this, it moves with a velocity which is q infinity. So, therefore, if I have an x t diagram, so let us say x and t. Okay. So, this is basically a equation of a straight line, and for various values of c, which corresponds to various values of delta rho naught, isn't it, which taken that as a constant, we will essentially have different sets of lines. So, if I were to draw that on this x t diagram, for example, say dx dt is this. So, I will have a straight line which is like this, okay, and that c is here. So, essentially say, let us say so for at t is equal to 0. So, okay, let us see over here. So, say at t is equal to 0. Okay. So, c is equal to x naught. So, let us say this is x naught. This is my x naught, okay, and the slope of this line, is one by q infinity, isn't it? Because dx by dt is q infinity. Okay. So, slope of this line by in this plot is actually dt by dx, if you look at this plot. So, what I have is a line like this. So, again if I take another value of this c, which depending on, instead of this being say rho naught 1 for example. So, I will get one more plot. So, I will actually get one more line. Okay. So, let us sort of let's say we'll do it over here. So, say this is my slope, right. So, okay. So, in here this is actually the slope is actually 1 by q infinity. Okay. So, then what we get over here is a series of line right, and each of the here, and the slope is same. The slope is same for all these lines, isn't it? It's just that this value is changing. Okay, that depends on this delta rho actually. Okay. So, what we see is that the solution that we got from here in for the finite wave is, we see that it basically emerges into several lines, several straight lines, right, which means that on every line the particles, right, on each wave all the particles are traveling with the same velocity, isn't it, dx by dt. So, on every line here the velocity is same. Now, this is different from what we saw for our actually finite wave, right. So, what we saw over here was that the particles in the wave all travel differently. On one particular wave the particles are traveling differently, they change with x as well as with time, right. All the particles are traveling differently. But if you look at the solution here, which we numerical solution that we got, is that all the particles on a particular line are traveling with the same velocity, okay, which is q infinity. So, that is basically the difference between the finite wave and the linear perturbation theory, acoustic waves here. Okay. So, now this is the picture. So, let us sort of redraw this picture this way. Okay. So, let me sort of redraw this, that is for a reason. So, now okay. So, this is say x and t. So, I essentially have a series of waves like that. Okay. So, they all have the same slope. Okay. So, let me just say draw the slope over here, which is 1 by q infinity. Okay. So, now and say this is x naught. Okay. Now, what we had taken is g is equal to 0. So, now in this case what we call this okay. So, we'll come to that later on. So, we said g is equal to 0. So, instead of g, now we can also we will do the other way around and we will say that f is equal to 0. Okay. So, what we will do is we will do the same thing and say that f is equal to 0. So, we will basically get the same procedure to do this, and then what we will get for the solution for f is equal to 0. So, if you see, so essentially what we will get is that x is equal to this is equal to a constant. Okay. So, let that be say c dash. Okay. So, what we get over here therefore, our solution is okay. So, therefore, what we actually get over here okay, I am trying to get basically the same picture out here. Okay. So, what I get from there is this. that this okay and this. So, let us just say this is negative x naught, okay, and the slope of this is nothing but that is all. Okay. So, therefore, what we see over here is essentially that this is moving, just the direction is opposite. Okay. So, what we call, if you look from here in the x t diagram, okay, so therefore, this is actually called a right running wave. Okay, this is a right running wave which is moving with this q infinity velocity, and this is a left running wave. Okay, this is a left running wave which moves with a negative velocity. The negative is basically the direction. Okay, so the solution that we get from the linear perturbation theory is essentially this. Okay. So, now, which is q infinity. Okay. So, now let us do something else. Now, we know, okay, so we know that now if you look at this, that q infinity, the way we defined it was del p del rho, right. So, in this case we okay. Now, we also define this as velocity of sound, isn't it? Because in this case we said we have assumed that our perturbations are very small. So, which means that we are really talking about very weak waves, weak disturbances, or we are basically saying that we are causing the disturbance by sound waves, and therefore, we can say that this q infinity is basically speed of sound, because that is how we define this is also the expression for speed of sound. Okay. So, therefore, we can say that all these waves are essentially moving with the speed of sound, okay, and the solution gives us this picture. Okay. The difference between the finite wave and this is that here particles on a particular wave are all moving with the same velocity, unlike in the finite wave picture. Okay. Okay. So, now, okay, let us do a little bit more on this, and then we will kind of move to other questions. Okay. Okay. So, having done this, now let us say the okay, so we can do the same thing for. So, we did all of this for say delta rho, isn't it? We got this solution, we understood this for say delta rho. Okay. Now, we can do the same thing for the perturbation and the velocity as well. Okay. Now, let us see, let us sort of just check that and see the relationship therefore, between the velocity change and the density change. Okay. So, if that gives us any more information. Okay. Now, so therefore, we will do a little more math here. So, we basically said that delta u is f. So, anyway, I am going to write q infinity, but this is actually the speed of sound. Okay. This, right. So, now again let us say that let us say g is equal to 0, right. If I say that, and then so then we will just say right. So, we will say del del u is that, okay, and okay, and also delta t. So, delta t is minus q infinity f dash. Okay. So, therefore, if I incorporate that here, so this is equal to minus q infinity. Okay. So, that is essentially what I am sort of looking for here, that okay. So, okay, so let us sort of write it in this way. Okay. So, this is equal to okay. So, this is the tail out there. Okay. So, this is what we get right now. So, we have this linearized continuity equation. Where did that go? Okay. So, we have the linearized continuity equation over here, right. So, we have basically what we are trying to see is that if there is a perturbation in the velocity, right, which is how we create the wave, what happens to the density? What is the connection? How are these two related, if at all? So, what we did just now is we found an expression for this delta this delta u del x, right, in terms of delta t. So, if I use that into this acoustic equation, so then what we get is this. So, what we get, so this essentially right. Okay. So, okay, I am not rewriting the equation. So, I will just straight away. So, put in for delta u del x, I will put in this, which gives me okay. So, if I get this, then okay. So, what essentially I will get from here is that I can write it delta rho minus right. This is what we get. So, what this means, so in essence what this means is that if I do this, what this means is that delta rho minus rho infinity by q infinity delta u is equal to 0, or delta rho is equal to rho infinity by q infinity delta u. So, this is essentially the relationship. Okay. This is essentially the relationship. Now, again, so delta p delta rho okay, is equal to a infinity squared. Right. Now, if I then incorporate this into this, then what I get is I will leave you to do the detailed or simple math now. So, essentially what I am going to do is incorporate this into this. So, what I get now is delta u is delta p by rho infinity a infinity. So, I get this. Okay. This. Okay. So, let us just remind ourselves. So, what we did was we took the delta this solution. We took this solution and did the same thing as we did for this. So, at first we said let g be equal to 0, which is what we did, and then we sort of worked with this and incorporated this term into the continuity equation, okay, the linear perturbation theory continuity equation, and what we combined this expression for the speed of sound, and we came up with this relationship. Okay. Now, we can do the same treatise by saying that this goes to 0. Okay. We can do the same thing with that, and what we will come up with okay, with for say f is equal to 0, what we come up with there is essentially I can write this as, so in here. So, basically let me sort of write this totally. Okay. So, say delta u is this, and again this is equal to Okay. So, what we see over here is actually for a disturbance or a perturbation in the velocity of delta u, the connection of that, what the connection of that with the kind of pressure perturbation and the kind of density perturbation, right. So, if there is if you disturb the flow velocity in this fashion, it will create a disturbance, it will create a perturbation in the pressure and density in this fashion. Okay. So, therefore, what we can see over here. So, now plus if the velocity, if delta u is plus, okay, so that means it is a right running wave. If it is negative, then it is a left running wave. Okay. So, in here delta u is positive. This is positive, and in here delta u is negative. So, therefore, delta u is essentially for a right running wave. So, let us just try and understand what this information that we got here, what does this mean to us. Okay. So, essentially what we are saying is, if delta u is positive, then it means a right running wave. Okay. And if this is negative, okay, then it is a left, it's a left running wave. Okay. So, essentially what we are saying is that delta u is the perturbation. So, therefore, when it is a right running wave in this case, okay, now if this is positive, okay, it essentially means that the perturbation is in the direction of the wave. Okay. Delta u is actually in the direction of the wave, and if it is negative, essentially means the direction is opposite to the wave. Okay. So, in here, so say delta u is positive. So, then I have a positive delta p and I have a positive delta rho. Okay. Now, what does that mean in here? So, say delta rho and say so delta rho. Okay. So, it is greater than 0. Okay. So, we have a perturbation in the density and pressure which is positive. Okay. What this means is that there is a condensation. Okay. And if it is negative, then it is called rarefaction. Just think about this. So, I have a certain wave, right. So, I have a certain wave. Okay. So, say this is a fluid which is moving, right. Now, I perturb this. Okay. I apply by a velocity which is positive. So, the perturbation is such that this is the velocity with which is moving. Because of the perturbation, suddenly the velocity pushes it this way, because the plus u is in the direction of the wave, right. So, if this was moving this way and then I perturb it, so it moves in this way, what this does is condenses it. The pressure and the density of the fluid now increases from what it was when it was moving like this. Okay. Let us do that again. So, you have a fluid moving like this, you perturb it. So, you see it condenses because the pressure and the density increases. Instead, now the fluid is moving this way. Okay. Now, the fluid is moving this way, and if it is moving, you apply a delta u in a direction which is opposite to that of the wave. So, I have a fluid moving this way and I apply it this way. What did I do? So, it kind of fans out, right, it spreads out a little more. So, therefore, the density and the pressure actually, so the perturbation actually decreases. Okay. It decreases, it is negative from the ambient. Okay. So therefore, if I have a wave which is say moving this way and I have a delta u like this. So, what that will end up in rarefying. So, this is a rarefaction. Okay. So, this is how a wave actually travels. Okay. This is how a wave actually travels, and this is what we see from our right running wave and left running wave and so on and so forth. So, now basically we have enough information about say a weak wave, which is our sound wave. Okay. Now, what we have done essentially so far is that we set out trying to study waves, how waves travel and so on and so forth. So, then we said we are going to incorporate small perturbations into it, and we were able to do that, and then we assumed that the perturbations are very small. So, that the wave is that of a very weak sound wave, and we have certain information regarding the numerical solution and all that. Now, the next thing to do, however, is to check, is to see that if we can actually go ahead and solve the governing equations for a finite wave, where we do not assume that these are very small. Okay. When we assume these to be very small, then we say it is sound waves, and we have gone ahead and done this whole treatise, which is interesting. Okay. Having said that, though, what if we do not assume this? Will we be still able to solve those equations, and will we be able to sort of get more information out of it? Yes. So, what we will do is not assume this. We will not assume this, okay, and we will deal with this instead of this. Okay. So, we will deal definitely with a finite wave. So, this is my finite wave. Okay. So, okay, I think we will just sort of begin this and take it take it forward in the next lecture. Okay. So, let us see how we can go forward with this. So, we will go back again to our basically our governing equations, right. We will go right back to our governing equations, and so what happens here is that delta rho is not, is not, this is not true, okay, is not less than rho infinity, and delta u is not less than this. So, what we get now is essentially finite waves. Okay, what we get now is finite waves. So, now let us go back to our continuity equation, which says okay, and then we also said, like in the last lecture, we will represent a thermodynamic variable, okay, and using this we also got, and this is isentropic. So, the change in density is 0. So, therefore, ds dt is 0. Okay. So, what we got from here was okay. So, we got this. Okay. So, therefore, okay. So, what we will write over here is that now when I get from here, actually what I get from here is that dp here, if I look at this, okay, and the other term which is del p del s into ds. Now, that basically this will go to 0, is not it, because we have because this goes to, this is an isentropic process. So, basically we are left with this, and we know that del p del rho is 1 by a square. So, we can incorporate that here. So, this can be incorporated like this. So, therefore, what we have is this, that dp is 1 by a square d rho. Okay. This is what we have. So, therefore, I can write it like this, dp dt is or what did I say, why d rho dp? Oh, okay, all right, doesn't matter. Okay, so I can write it like this as well. Okay, so now if I, so basically I can write this in a similar way. Now instead of p, okay, instead of p written in terms, this is what we had done earlier. So we can also write, say, a density, right? We can also write density in terms of p and s. We can also write the same thing, same treatise. Then in that case, we can also write as, say, d rho dt is actually in that case it will become a square, right? Yeah. So, this is a square dp dt. So, we will just use that because this is what we need here. It is the same treatise. We can write one thermodynamic variable in terms of the other two state variables. In this case, the ds, it is isentropic. So, ds is 0. So, therefore, we can write this d rho dt is this. Okay. So, now if you look at this equation here, so basically I have an expression, this d rho dt I can write in this form, isn't it? So, if I do that, okay, so what we will get is this. So, we are going to basically introduce that this expression into the continuity equation and see what we get, right. Okay, so, so essentially what we will get is right plus this is what we get, and let us write this for a one dimensional case. If I do that, what I will get is this, right. Okay. Okay. So, this is what we get from here. If I write this for a non-dimensional for one dimensional case, let us call this as 1. Okay. Now, I can again, you see I have this momentum equation. Now, from the momentum equation what we get is that this is what we get from the momentum equation, and we will write this again in terms of if for a one dimensional case. So, again what I get here is, so what okay, so okay, I will rearrange this, I will write this for a 1D case, okay, and rearrange this. So, what I get here is essentially this. Okay. So, this is what I get from the momentum equation. So, this is essentially it. Okay. Now, what we will do in the next lecture is take these two equations. All I have done here is just taken the governing equations and I have written them in a form that I am going to use, and it is going to give me some more information. So, all I will do now is take this and this equation and sort of work with this. Okay. I will not start from here. So, what we will do is essentially this is actually the step where we introduce the method of characteristics. Okay. Now, method of characteristics is a very strong tool in how we solve problems in especially compressible flows, right. And we will see if we will be able to get make some headway into getting us a solution for the finite waves. Okay. So, we will continue this in the next lecture. Okay. Thank you.